I think this is stabilized. Let's start. So my name is Rodríguez Wenning. I'm legal counsel at the World Wide Web Consortium, but also at the European Research Consortium for Informatics and Mathematics. I have 20 years in metadata on my shoulders, but mostly concentrating on legal metadata. But today we have all kinds of metadata because we want the metadata to be interoperable. Metadata comes in many flavors. And today we talk bazaar. We don't talk about nice cathedrals that engineers like cathedrals. They like to know what is going on. Their systems totally control. And I remember Tim Berners-Lee when he was telling people, the hypertext people, that he will have an open system. They said it will never work. But today we know how to live with 404 not found. So we are a bit in the bazaar, and how this bazaar is built, and what is still missing in the bazaar, how we can do this. Pierre-Antoine will introduce the concept of linked data, kind of for those who are not fully and deeply into it, and also present some of the newer developments in that area, because I think linked data will help us to solve some of our issues in interoperability, not all of them, but some of them, and they are one of among many. Víctor will tell us what we can do with data annotations. So linked data can be used to make data annotations, and Víctor will tell us data annotations can be a huge tool and can do many things. And so the Lynx project was pretty instrumental in bringing up new solutions. And Svetla is then extending this from annotations to the generic use of metadata ontologies and things in the healthcare sector, where I think it's absolutely crucial, because we have all the administration, but also things that we need to accomplish and to have with metadata. And of course, it needs to be interoperable, and there it needs especially interoperable because it must be not error-prone. Mistakes have to be discovered, and so on and so forth. And finally, we'll have Piero Bonatti. Piero will join us a bit late because he's currently having a lecture at the University of Naples. And Piero is my policy guru. He knows how to model the annotations so they become a policy, and how to use this policy to control data, to control metadata, to control data flows and data handling with reasoners and other algorithms. And Piero is really cool because he kind of translates things into legacy systems and back into metadata and so on and so forth. So, but let's hope that he's coming in time out of his lecture. So we would then start with Pierre-Antoine. And Pierre-Antoine, could you please start your presentation? I will stop my video and mute.
Can you see it?
Yes.
Okay, wonderful. Thank you, Rigo. So I'm Pierre-Antoine Champin. I'm currently working as a researcher at ERSIM and at W3C as a fellow. And as Rigo announced, I will be presenting the principles of linked data, as well as a number of perspectives currently worked at W3C. So as we know, that's what that's the topic we're gathered for today. Metadata, data in general, and metadata in particular, comes in many flavors, is highly heterogeneous. I think among the 3 V's of big data, volume, velocity and variety. I think variety is probably the one most prominent in the case of metadata. And so in this example, I represent several data formats. As we will see, formats is just one small part of the problem. And so linked data is a set of principles and standard technologies to address the problem of variety and help to reach interoperability of many kinds of data, but is well suited for metadata. So the first step towards interoperability is recognize that the data structures underlying those different formats are heterogeneous, but can be captured in a more general structure, which is the graph structure. As we know, graph databases have become quite mature and very popular in the past years. And the reason is that this is a very flexible and powerful data structure that can cover the different specific structures of different formats, like the sequence of text files, the trees of XML or JSON files, or the tabular structure of CSV files, for example. So the first step towards linked data is to look at your data, not in their native, more constrained structures, but in the generic structure of a graph. Then those graphs will be labeled, be it by the tag used in an XML file or by the columns of a CSV file, or again by the attributes of a JSON file. And those labels are usually small strings of text. The problem with those labels is that their meaning is highly contextual. And I said that formats is just one part of the problems, because even if everyone was using, say, JSON, then the labels in those JSON files, so the attributes in the JSON objects, would have different meaning depending on the source of the metadata. And in this example, for example, we might have an intuition that creator on the left and author on the right actually represent the same thing. But another problem, and maybe a more serious problem, is that source on the left side and source on the right side might very well represent different things, despite the fact that they're using the same label. So in order to achieve interoperability, we need to move from those simple contextual labels to context-free labels, labels that whose interpretation does not depend on the context, whose interpretation is shared by everyone. And the good news is we already have something that works pretty well for doing that, and that's URLs, also called IRIs in some contexts. But for this presentation, I stuck to the more commonly known acronym URL, and even if there are some subtle technicalities involved here, I mean, if you never heard of IRIs, you can just think of them as URLs. So URLs are indeed globally unambiguous. The same URL has the same meaning everywhere you find it, regardless of who finds it, where they are, and what software they're using. Okay, the same URL basically points to the same thing wherever you are. So they are context-free identifiers. They also have a number of good properties. They are managed in a relatively distributed way, which helps have this kind of system scale. We cannot rely on a central authority defining all the URLs for everyone. There will also always be some corner case that is not provisioned for by such central authority. And so we need those URLs to be able to evolve in a distributed way, so that everyone can have the URLs they need to represent their metadata. Despite that, URLs have a single source of authority. That is, every URL has an owner, so to speak. Again, there are some subtleties involved, but and that owner, the people that has the power to create that URL, to put something behind that URL, is the authority for the meaning of that URL. And finally, URLs are usually actionable. That is, you can actually follow the link and get some content. And good practices in linked data mandate that the content behind the URL is actually describing the meaning of that URL, the meaning to be that this URL has in a linked data graph. So that content can be human readable, that could be a simple HTML page, or it can be machine readable, that could be some RDF describing the meaning of that URL using ontologies or things like that. Of course, one does not exclude the other, and the best is, of course, to have both the human readable and the machine readable description of the meaning of that URL. Actually, and as a parenthesis, this is the way schema.org works, by encouraging people to embed a small piece of linked data as microdata or JSON-LD inside HTML pages, so that those HTML pages are equally understood, well, equally, but okay, at least are understood to some extent, both by people reading the page or viewing the page in the browser, or by machines reading that piece of embedded data. So we have those URLs that are context-free identifiers, and then we can map the contextual labels used in different metadata sources to unambiguous URLs. And so on my left graph, in my examples, if I come back to this, okay, I had 4 different labels, 3 labels on the graph on the right, and so those labels can be mapped individually to unambiguous URLs. And here I can see that creator on the left and author on the right both map to the same creator term by the Dublin core vocabulary. If I don't know about that term, I can still follow the link and see the documentation of the Dublin Core initiative explaining what exactly they mean by creator. On the other hand, source on the left means source according to Dublin Core, while source on the right means derived from according to the provenance ontology. So same local contextual label, but different meaning represented by different URLs. So those URL, the meaning of those URLs can be dynamically discovered by following the link, provided that the authority behind the URL followed the good practices of documenting its meaning. But what about finding URLs to express what I want? So there are a few services out there. One of them is the linked open vocabulary, which is very nicely named LOVE. This is an index of existing vocabularies that are published on the web, and you can find the terms that you need in order to discover URLs that are useful in your context. So that's one way to discover vocabularies a priori, and if you discover them a posteriori, you can still follow the links. So now we have replaced the labels on the edges of our graphs by URLs that are ambiguous, but the same can appear for nodes. Nodes also denote things that the metadata is about, and some of those nodes describe things that are specific to a given metadata source, but other nodes may be shared across different sources, and that can be discovered if we use the same URL to identify the same object, okay? And if we do that, then we get the real value of linked data, because those things can be linked, and those nodes in the graphs can be merged, and then we have a single graph containing information from different sources, and that's where interoperability really shines, okay? Thanks to the network effect, we get more value from this merged graph than from each source of data individually. So that's, in a nutshell, the principles of linked data. And so it's tempting to say, okay, so that works. We have those technologies. We have open source implementation. Those are standards. Let's throw away what we have and replace all this by those brand new standards. Well, they're not so new actually, but with those beautiful standards. unfortunately, we know that it's not the way it works. Okay, we can't have people throwing away a stack of technologies that they've been using for a long time and that works for them. And there are very good reasons to keep using those old technology. If only the legacy of having applications built for those legacy formats and working very, very fine. So what I think is the real added value of linked data is that it is not meant to replace existing technology. It can be used like that. You can, of course, convert your data once and for all, put that in an RDF triple store, and use only linked data from now on. But there are also other ways to do that, and that's what I like to see as putting linked data glasses whenever you need them. That is, you still have your XML data on the one hand, your CSV data on the other hand, but whenever you need to interoperate, you want to look at them as an RDF graph. And for that, you will attach contextual metadata. Well, in our case, if that's metadata to start with, that would be contextual metadata that explain how this legacy data in other formats can be interpreted whenever you want on the fly as an RDF graph. And we also have standards for that. Gridle is a relatively old standard, not as used as it could be, I guess, but still implemented for describing this kind of contextual metadata for XML files and converting them into linked data graphs. We have the same for CSV. There's a set of standard called CSV on the web for expressing that kind of contextual metadata for CSV files. And of course, we have JSON LD, which does the same for JSON data. And so, so linked data is not, again, a replacement standard for everything that already exists. Okay, it's a layer of interoperability on top of existing data that doesn't replace it, but allows it to consider whenever it's required, whenever it's relevant, as those unambiguously labeled graphs that can be connected to each other. So that's basically a summary of those principles. We unify various data structures with graph. We replace ambiguous local, well, we map ambiguous local labels to URLs, which can be agreed upon a priori using a vocabulary discovered in the love index, for example, or discovered dynamically by following the links. Now, a few links to ongoing work at W3C about what's coming next. Okay, well, first, there is a candidate recommendation, so it's almost a standard, called decentralized identifiers. I very briefly alluded to the fact that URLs are mostly managed in a decentralized way. That's not entirely true, and basically because of the domain name system, which is essentially centralized. And most of the time, it's good enough. It's a good enough decentralization for many uses. But sometimes we need real decentralization, full decentralization. And for that, the decentralized identifier proposed recommendation, provide a new kind of URLs that are not meant to replace HTTP URLs, but to complement them, which allow for a fully decentralized minting of identifiers without any requirement for a centralized component, and so enhancing autonomy and data sovereignty. And again, this is almost a standard. This is at the stage of a proposed recommendation. We have another recommendation in the making by the Data Exchange Working Group, which is a content negotiation by profile. I describe here two steps, okay, moving from arbitrary structures to graphs and moving from local labels to URLs. But this is, yeah, sorry, how much time do you have left? I didn't really check. You're muted, Rigo.
3 minutes.
3 minutes. Okay. I'll wrap up in 3 minutes. No problem. Thank you. So some interoperability problems remain, and that's because different vocabularies, different set of URLs used to describe a given domain exist and overlap. Okay, so given some information about a domain, there are several different ways to describe it using linked data. Even then, we still have some form of variety. Okay, and those different vocabularies can be captured by profiles. This this is still in construction, allows consumers to require the data using a given vocabulary, using a certain set of shapes. One of the motivation is DCAT AP, which I think many of you are familiar with. So that's also an interesting recommendation to follow that still reduces the gap and still improves interoperability. Signature is also an important part of this, and unfortunately, for 20 years, we never had a proper way to sign graphs. Not a given representation of a graph, okay, but sign an RDF graph, a linked data graph, regardless of how it is actually encoded. And it's all the more important with what I said about the fact that different legacy formats can actually be considered as graphs. So it's important to be able to sign a graph regardless of the fact that it's represented in RDF XML or Turtle or in a legacy CSV file. And this working group doesn't exist yet, but a proposed charter is currently being discussed, and hopefully it will be approved in the coming weeks. And finally, RDF Star is a proposed extension of RDF, not a working group yet either, but a community group as a proposed specification in order to extend this graph model to make it even more flexible by allowing relationships not just before nodes, but also relationships between edges of the graph. This can be worked around in current RDF, but there's clearly a need for more flexibility and for being able to represent that kind of thing. So those are the things that W3C is working on at different stages, and that can be of interest to you if you want to use linked data. Thank you for your attention.
Thank you, Pierre-Antoine. So just stop sharing so that Victor can bring up his slides.
Hello. Thanks a lot for your presentation, Pierre-Antoine. I will support some of the messages you have just delivered. So if I'm not wrong, I'm sharing now my screen. And now you can see my presentation.
Yes, and I encourage everybody in listening to us to use the chat functionality in WOVA to put questions there, to discuss there, to make remarks saying Victor needs to see a barber or something like that. Okay.
Mm-hmm. Okay. Thanks a lot, Rigo. Thanks a lot for this invitation of being here. It's my real pleasure. I hope I will make this presentation useful because I will talk from the experience. I am here acting as the scientific coordinator of the Horizon 2020 Lynx project. It has just finished, and I will tell you the lessons we have learned. I will first show you the metadata-related Lynx achievements. Then I will be able to share the lessons learned. How would we do things again if we had to start from the beginning? This is something now we can do because the project was evaluated last week, so now we are free to speak. We did great things, but also we made some mistakes. I'm here to share the mistakes today, which are usually more useful. And finally, I will pose some questions to this educated audience to foster debate. The Lynx, first of all, of these three parts, the Lynx project. This is a project, as I said, this was an innovation action, so it was not research. It finished in April. It was evaluated last Thursday, actually. It was coordinated by my institution, UPM, by Elena Montiel, and I will give you some technical insights. The results of these projects are four. The first result is the multilingual legal knowledge graph, which has adopted every good practice that Pierre-Antoine has just described, and it's a graph connecting heterogeneous documents such as European directives, industry standards, national legislation, case law, legal documents in general, and terminological data, dictionary data, language resources, right? In order to do so, we have adopted common standards such as concept schemes in SCOS, Ontolex Lemon, lexical information, etc., plus a new type of document that we had to define, that was the Lynx document, that could be abstract enough as to represent all this variety of data formats. Having a very good collection of heterogeneous documents represented in a common data structure, we could develop services. So the second main result of this project is the Lynx service platform, which is a collection of 18 services that perform NLP operations over these documents, generating rich annotations that are not present in the original source, the original law, etc. So we could identify entities of temporal entities, companies, etc. But we could also identify which are the key concepts, which are the different parts, and also we could execute very fine-tuned search operations, question answering, etc. Each of these services was accepting this Lynx document as an input and was offering another Lynx document as an output, but with annotations. It was very beautifully described with HTTP REST APIs, each of these services, operating in different languages, very well documented. It's a good result, very good result. So, once again, the overall procedure is to harvest original documents, create a naked Lynx document, run some enrichment workflows, and get some new annotations. Heterogeneous documents are harvested, made uniform, and enriched. We devised a very complex architecture for the workflows using Camunda and BPMN. Everything is standard. And these technologies were applied in 3 different use cases. In the domain of labor law, in the domain of geothermal energy, in the domain of contracts by different companies with the intention of exploiting these results. So these companies were in charge of making the beautiful interface, able to represent these annotations, etc. Very good, very solid work. So the last of the results I am presenting is the data model itself, the Lynx document, which is a structure that was made in RDF with a beautiful JSON LD representation, following very good practices, such as defining shackle shapes to make validation. I think it's a very solid result as well. And this data structure is compliant with NIF, which is the NLP interchange format. So these documents can be directly parsed by other tools, which is very nice because this session is about interoperability, isn't it? Metadata records were using also standard specifications such as the ELI metadata, European legislation identifier, whenever it was possible, and some other standards in the legal domain. Annotations were the main, were the output of the services, and were also fully NIF compliant, the NLP interchange format. So all in all, everything looks very solid. It is very solid. And we made a huge effort in producing the beautiful data model with a Lynx ontology, but we invested a huge amount of time making the perfect data model, right? So in these minutes, I think you have learned about the achievements, but in my opinion, it was very expensive, the achievement of this data model. I will come back to the previous slide. Making an ontology which is well supported by competency questions with ontology requirements, specification document, with a lot of iterations, because the ontology is developed using software repo, GitHub, to debate each of the changes through issues. It's a very, very costful operation, especially if it's involving 10 different partners and each of them pose different considerations and requirements. It was an operation that was extended during several years. It was not even finished in 1 year. And all in all, it's a lot of money invested by the European taxpayers. And I'm not sure if many will adopt this ontology after the project has finished, right? So if the observation is that we have invested a huge amount of time making the perfect data model, if we had to do this again, I believe that we would apply standards only for the interfaces. What we did is adopt the standards as the internal data model of all of our services, right? So we spent a lot of time making our tools, our services, the services that we have been developing in this project, to work natively with the standard documents. Pierre-Antoine said, I don't remember his sentence literally, but he said that the link data shows its best phase when it's just the interoperability layer. It's not here to replace existing data models, right? So in this project, we had to devise a new data structure because we had peculiar requirements. None of the existing data models was making us happy, so we had to do it, right? But I believe that the emphasis has to be made only in the interface, right? So my advice, the lesson we have learned is use the data model that is most convenient to you. Do not spend much time in implementing standards, because this is very costful for the internal operation. Instead, define your own data model in a faster way and then focus about interoperability in the import-export part, right? All our documents that we have produced are available as link data, as Pierre-Antoine said, available to be queried in Sparkle endpoints. It is published using the link data platform interfaces, but it was not a requirement that this data model was used for the services, right? So, lessons learned, standards for the internal data model may not be the best approach. Rather, make export-import from an internal data model to a standard data models, right? Second lesson, I have 3 lessons. This is the second lesson now. Second lesson, data dies, but methods survive. Every castle is down at some moment. So in this project, we have created very nice data sets. We have collected legislation from Ireland, from Spain, from Austria, from the Netherlands, from a couple of countries now I'm forgetting, different jurisdictions. So we have created very good data sets. But these data sets will become soon old, deprecated, and what will remain is the methods. So focus on the methods, the data is secondary. Third lesson we have learned is that our metadata bilingual speakers were the most valued experts. We were a working group, very heterogeneous. We were 10 different partners. One of the partners was expert in machine translation. Another was a semantic web company, expert in semantic web technologies. Other partners were experts in other different areas. And their knowledge was very deep in one specific domain, standard, etc. But it was not so productive, their participation in the meetings, if they didn't know about the others. So the Babel Tower was not finished because there were no bilingual masons or constructors here, right? So we wished we had more metadata bilingual speakers. So if I can make now pose 3 questions for a debate, I would like you to consider these 3 questions. Whom to report public data models? We have made, okay, now we have made the effort. Now we have a very nice data model with shackle shapes, validation, APIs to validate that are up and running, and you can test, you can try, you can adopt this model. You can adopt this model. But I do not know which is the right audience to disseminate my message. So it's a pity that it will be wasted this money if the data model is not used. So whom to report public data models? We are under the umbrella here of BDBA. Perhaps this would have been a good opportunity. Second, how to identify who are the metadata bilingual speakers. So perhaps BDBA could have acted as an index of experts in different technologies, and we could have identified more easily who were the key persons. So my question in this, my third question in this forum is, how could BDBA have helped in these 2 questions? How can you do it better for the next time? And that's all I wanted to say. And I finished my presentation here. Thank you.
Okay, this leaves us 7 minutes for a question for answering your questions. If you put them on slide again, or start the discussion.
Yes.
So I'm particularly impressed by the bilingual speaker, because I was in this competing special project, which did something also with legal stuff by trying to build a data protection system. And to answer your question, we created a community group in W3C, which made the vocabulary available. And this is the same, because I think you had a huge effort, because we are the first ones to do this. And you cannot, we looked for something to reuse. There was nothing. And one of the interoperability things here is I think that we can gain a lot of time by making those data models that you just created reusable, because I'm not sure when you do this in the middle, your own thingy, it will work, because your data model has knowledge in it, has insight. And to gain insight, you translate it into the data model. And the lawyers can babble and babble and babble. You get them to materialize their concepts only when you push their head on the data model. And then this is the moment of truth, you know, where they can't escape. And so I'm not surprised that it took more time. Somebody else wants to respond, to comment on the panel? Okay, in this case, Pierre-Antoine, just put your camera on.
Yeah. Yes, thank you for the presentation. Actually, more of a comment, not specifically on those questions, but I wanted to react on the interface thing and do whatever you like inside. I agree, it's a good approach. I just wanted to point out that the work, so you explained that you spent a lot of time designing the perfect model, right? And I think the work to design the perfect interface should not be underestimated. Precisely because interfaces are what is seen from the outside, and so you don't want to mess that up. So I totally agree with you that that it allows to separate the concerns between the internal works of what you're doing, and indeed we agree on that this doesn't have to be standard compliant all the way to the core of the thing. Of course, everything that standards can help should be used, but it should not be it should not be mandatory if that's not the best way to go. But again, it's a lot of work to design a good interface, and so that's not a silver bullet either. Just wanted to point that out. But
yeah, I think you're right, and I will launch another message. I also co-chair the ODRL W3C community group, and so I know some of the W3C specs very well, and I do appreciate a lot when W3C specs have the ways to verify if a piece of data is compliant or not with certain standards. So if you are now in W3C RDF-based specification, please do include always shackle shapes in order to validate if something is conformant or not. This makes the life of implementers incredibly easier. So in our case, we were working with NIF. This is the NLP interchange format in this Lynx project. And we had not the means to determine if we were being compliant or not. And in the end, we had to go to the existing tools and say, oh, it works, it doesn't work. Shouldn't be the case, right?
Yeah, go ahead.
Yeah, I totally agree. And shapes are becoming more and more important in the Lynx data space, and I think it's a great progress. And again, I mentioned the content negotiation based on profile. I insisted on the vocabulary dimension of the profiles. That is, do I use schema.org or do I use Dublin Core for representing the same kind of relationship? But shapes are also a very important point. I can have two people using the same vocabulary, the same set of URLs, and use them in very different ways, and that makes interoperating with that kind of data quite difficult. And a profile for Lynx data is also a set of shapes that one is complying with, so that I know what kind of Sparkle queries I can write and what kind of data I can expect to be always there and what are optional and so on. So yes, big plus one on that.
Yeah, just to report and to finish before the next presentation. When we had this project, I remember that we came with our Lynx data tool chain tour to a telecommunications operator who had a totally optimized real-time database, and we came with our tools. You know, after reasoning for 2 minutes, the thing would come to a result. They said, "Are you crazy?" and there goes your import-export. Because it was absolute for the annotations for the annotations that we need in metadata. It was crucial to have the mental model of property graphs of RDF star of RDF, this mental annotation model, and then to translate that into real world is sometimes import export, but sometimes it's easier to just take a standard parser and a standard tool that hangs around somewhere and which you can use quickly. Which brings us to our outlier, Albert, who is presenting the automotive metadata model, which has been developed in a say, really apart from what we are talking about so far here, because so far this was the nice W3C RDF model that was created in a certain academic environment, but here we are industry, and they have chosen a certain way of doing things because it fitted their needs. And it's very interesting to see the differences and also to see what they are doing. And it will be challenging to see how we make that interoperable, but because we need to. Okay, Albert, please.
Yes. Yeah, thank you very much, Rigo. My name is Albert Zilverberg. I'm working as a scientific assistant and researcher for the Institute of Applied Sciences in Bremen, or short ATB. And I also want to talk about data models, but a bit in a different fashion as in the previous presentations. So here we have the cross-CPP project, which we are looking at So its topic is standardization challenges in cross-sectorial data streams. So to have a bigger picture at the beginning, here are 3 data platform projects which are in a row, big data platform chain projects. So the aim is to give data customers access to CPP data. So by the way, when I talk about CPP, I mean cyber physical products, which could be anything like a car or a plane, a mobile device which has sensors, and enables some service providers to build services upon this cross-sectorial data streams. And the other goal is to empower the data owners to exploit their most valuable asset, which is, of course, the CPP data, which he or she is producing currently. And the journey started in the Automat project, where we had Volkswagen, Fiat, and I think it was Renault as partners, which could provide data coming from their vehicles. And there, the aim was to build a big data marketplace to share this data with service providers, which could then build their services upon this data. And there we also started to build a first common data model to structure all this data coming from vehicles into one brand-independent format, which then we called the CVIM, which was the Common Vehicle Information Model. And the cross-CPP project, which is the follow-up of this whole story, is then extending this principle of vehicle data to include data coming from all different kinds of cyber physical products from all industrial sectors which you could think of. So in the consortium, we had, for example, Volkswagen, but also Siemens, which could provide us data coming from home automation systems, which are located in smart buildings, for example. So, and then we have the third project in a row. It's also about big data platforms, but a bit in a different fashion here, because it's not about building a big data platform for sharing data, but it's more about how different data platforms can interact with each other in terms of what kind of policies and conditions have to be in place, speaking of contracts, for instance, and also how secure and controlled sharing of data streams can be ensured. Here we have envisioned some data traceability solutions. But now coming back to the unified data model I want to speak about today. So when we have a look at the current data landscape, which we can see today, on the left side, we have the data provision side. And the situation is that we have only limited data access. So we have a lot of data access constraints within the OEMs, which means third parties have really difficulties to access this data, but they want to. So they really want to have access to this cross-sectorial data streams. But the problem is every OEM has his own brand-specific data format, which he will use only for his own application and services, of course. So the data exchange across the platform is very brand-specific at the moment, and of course, for an external service provider, not feasible and very uneconomically, because he would have to build an interface to each of these brand-dependent platforms from the OEMs. So when we look at the other side, the service provider needs, so what he really wants to have is he wants to have a brand-independent data exchange for sure. And what would be really ideal is to have just one single access point to get the CPP data from the marketplace, which you can see in the middle here. Which is the negotiation part of the whole process. And so this would be a really win-win value chain for the service provider as well as for the data provider to have this unified data format in the middle. So the key question is, of course, how can we bridge this gap here? And this is the point where the common industrial data model comes into play, which has been developed in the cross-CPP project and is follow-up of the CVIA project. And I want to take you now on a journey how this model is being built up and what are the conclusions out of it. So the idea is to have one common standard for all different kinds of CPP data. And yeah, one major feature is that the CIDM is open and highly scalable big data format and has been designed to harmonize all kinds of proprietary CPP data into generic data sets. So this means we can ensure brand independentness. It's open for the integration of diverse CPP data, and it supports also different signal and measurement types, as we will see on the next slides. And very important, it can also store information about data ownership. So about the person who really produces the data. So coming to the specification, we have decided to have a layered architecture following a bottom-up approach. So at the bottom layer, we have the signals, which kind of represent the smallest unit you can think of. It's a sensor signal measurement, which is generated directly by the cyber-physical product. And then we have on top a layer which aggregates the sensor signals. We call it a measurement channel. I will show you in a moment. And on top of that, we have another layer, which is the data package layer, which even another time packages the measurement channel and adds additional metadata information to this signal measurement. So starting at the bottom, the signal layer, as you know, the CPPs, they will provide these observations, which are raw sensor measurement and also CPP status information. And we have the situation that signals may vary between different brands, of course. So Volkswagen has not the same sensor signals as BMW, for instance, models. But even when you look, for instance, inside Volkswagen, there are different models have different signal configurations. So an ID3 would have a different configuration as in a sports car, for example. So there's also inside a company already some variety in the signals. So we have different value ranges, sampling rates, or also resolutions. So when we look what kind of signals we are dealing with today, there's a very basic text information, which could be, for example, the type of the CPP we are looking at, like a car or a building or a plane, mobile device, whatever. Then we have, of course, the numeric type, which is very natural. I think 99% are numeric because they represent the physical, feasible measurement values like temperature, humidity, all what you can measure with sensors. And then we have something like enumeration where there are predefined states, like a fuel type, or for wipers, we could have wiper on or off, or ESP system could be on or off. So these are the basic measurement signals we have. And so when you would decide now to send these signals at every moment in time to some backend device, you would have a lot of data, and it would cause a huge traffic on the data transmission side. So there are estimates that one car produces per day about 12 gigabytes of data. So apparently that's not possible to send this all in on one time, or every time the signal is being produced. So what we need is some compression methods, and some examples I want to give you on this slide. So very natural and I think well known is a time series. So what we have is every timestamp is referring to one signal measurement value, and depending on how you stretch the sampling rate, you can achieve a big compression already here. So I think there are a lot of services which could use this time series format for the services. But there's also another channel which we call the histogram channel. So what we are doing here is not for every signal observe the timestamp where the signal has been recorded, but we have bins, and the bins represent now the signal value ranges. And whenever a signal appears, it will fall into one of those bins. So what we then observe is not the real value of the signal during the time, but how often did a signal appear. So, and when you think of where this could be useful, for example, when you think of an insurance service, you know, telematic options are now very popular today. And the insurance wants to know, did the customer drive too fast in the city or on the highway? And he will observe, okay, he drove 55 or 60, then he does not really need to know when did this happen. But what really counts is how often did this happen. And for this, the histogram channel can be very, very useful information. And when you combine this information together with the geographic information, then thinking of a weather service, this could be really useful to have a map and the distribution of this sensor measurements. So on top the layer, if you remember, we have the data package, and here it all comes together, because here we add to the measurement channels also metadata, which makes the data packages searchable and indexable in the marketplace later on. And coming to the metadata, what can be added? There are a lot of different fields, like, of course, the reference to the measurement channel, what type, histogram or time series. Then the geographical information can be added. Also from the OEM side, a certification like checksums or sequence numbers in the signature. Some basic statistic properties which will be computed automatically, like minimum, maximum values and averages. Of course, the start and stop timestamps, and of course, very important information about who holds this data, what privacy level is in place, and information about the copyright. Yeah, and then of course, we have the data itself, as you saw on the previous slide, which can be structured in any of these measurement configurations here. So to have a bit the bigger picture now, and where really the interoperability comes into play is, so we have here the cross-CPP ecosystem as a whole. And on the left side, you can see that it represents the data provider side. In the middle, there's the marketplace and the cloud storage. And on the right side, we can see the service providers which are interested in getting this data. And here, really, the benefit of the CIDM comes into play, because when you look on the left side, there could be potentially hundreds or thousands of different data providers. And what they have to do when they want to share the data is they just have to transform in their backend when they send the data to the CPP cloud storage in the middle pillar. They have to transform the data into CIDM compliant format. Then they can send the data package as a whole to the marketplace. And when a service provider now approaches to the marketplace and wants to have this data, he already knows in what format it will come, namely in the CIDM format. And the service providers can rely also on this format, which means it will not change very much during the time. So this is really the benefit. So they have one single access point to the marketplace, and they already know, okay, when I get my data, it's in CIDM format. So here really the benefit comes into play. So, of course, then is the question, what level of harmonization is achievable by the CIDM format? And here we have different levels. So what has been developed within the cross-CPP project is to create an open and common ecosystem, which is completely working independently of any brand and services. And this applies to OEMs as well as to service providers. So the CIDM, as said already, is a common data format that treats all data in the same way. So it's independent of the OEMs. Every OEM, may be it a vehicle manufacturer or a mobile device app developer, they all have the possibility to transform the data into this format. So it's also independent of any source or data bus or standard, like we have this in cars for the CAN bus or OBD. And what CIDM also provides is a common signal list from all OEMs. So in the cross-CPP project, we did it for Volkswagen and Siemens. And we did the first step of harmonization between the signal descriptions. And where possible, the CIDM also derived a subset of common signals. So, for example, outside temperature could be measured in cars as well as in buildings or planes, or also in your mobile device, for example. So, but there is also, let's say, the horizon for the common vehicle common industrial data model, which is it cannot provide and should also not provide that all OEMs deliver only the same type of data, which is of course out of scope and also not of real interest. So yeah, as the world change, also mobile, also the cyber physical products will change. And this is why the CIDM is not a widget, but an open standard, and of course also open for extensions and modifications. So as well on the data provider side, the things may change as well on the service provider sides. There may be sometime be a bigger demand for some specific sensor values. So that's why, depending on the market needs, the data consumer community can extend the CIDM in respect to the following means here. So amount of the recorded signals, of course, and also modifications can be done regarding the type of the measurement channels which are being observed. And therefore, we have foreseen to have a standardization board which will then decide about these modifications which have to be done to this data model. And this board will consist of members from, for example, data provider side, from the marketplace, as well as members from the service provider side. So, and yeah, my last slide is ongoing standardization activities at the moment. So we have one partner in the consortium, which is the Open Group, and which has great expertise in setting up standardization activities for especially industrial standards. So we have some exchanges already with the SOSA forum. So SOSA is standing for Sensor Open Systems Architecture, and it's a standardization body dealing primarily with setting up new industrial standards. And we already have prepared the terms of reference to form a working group in the SOSA forum, and now also inviting industrial participation now. So, and further actions would be to have a SOSA format compliant specification of this model, and to really get in contact with the working group to finally adopt this public specification and make it ready for the formal submission. Yeah, thank you very much for your attention. If there are any questions, this is the time.
Thank you very much. So you mainly there is this other way. Hi, Piero. Piero is joining us. I hope your lecture went well. So this different approach is, while Pierre-Antoine has presented this kind of mixing 10 things together. I see in the industrial way, you say, okay, we get from everybody to a unified CDIM approach, and then we diversify back into the data markets. So a unifying approach. Do you think that we could also mix some vocabularies in, like the data protection vocabulary that's certainly needed in this context, at least when you go to the garage and get your maintenance done, and they see where you have been all the time?
Yeah, I think we can, of course. When we have a look, for example, here in this, do I share my presentation?
Yeah, we see it. That's now we see the presenter mode.
No. Yeah, I think here, this would be the place, when you look at the metadata we have here, we also could include additional information, of course, about the data, like semantic dependencies which are there. I think that would be the place.
Okay. Okay. Thanks a lot, Albert. I think it's time for, so please stop sharing so that Svetla can bring up her slides. And now we go from car to healthcare, and healthcare is special. It's really special. I'm coming from data protection side, and there's Article 9, which says anything in health data is sensitive, and it's you have to be careful. And now we're seeing attacks, and then you need high security and all that. So health data is really, really special. Svetla, please.
Hello, thank you for the opportunity to present today this session. My name is Svetla Bocheva. I'm from Sirma AI Trading as Ontotext, and I'm here also as a lead of the communication, dissemination, and standardization activities at Horizon 2020 project Aximode. It's my pleasure to present today a talk about metadata in healthcare sector. The project main objectives are to develop prediction and analysis tools for clinical settings and research, and to develop weekly supervised knowledge discovery algorithms for extreme scale data to associate visual content of clinical images and semantic content included in the diagnosis. That's why in the project we have two research organizations, University of Padua, two university hospitals, Cannizzaro Hospital and Red Belt University Medical Center, high performance computing company, Sarsara, providing infrastructure, and two industrial partners responsible for the semantic technology, Ontotext, and for the image analysis, Microscope IT. Clinical data are highly heterogeneous. We have electronic health records, clinical narratives, biomedical data, medical imaging results, especially in our project we're dealing with histopathological images, which are very rich source of information. Especially in healthcare, we're dealing with personal and sensitive data, and all these data should be in compliance with GDPR. Regarding the interoperability, we need to stress our attention on three different types of interoperability: health interoperability, technical interoperability, and semantic data interoperability. The core Dublin Core Metadata Initiative, of course, is one of those standards that is used. For healthcare interoperability are used HL7 and HL7 FHIR, and alongside with them for technical interoperability are used JSON and JSON LD. In order to be able to integrate with hospital information systems, different tools and services through APIs, and to exchange information with them. For semantic data interoperability, the core standards are, of course, W3C, OWL, RDF, SCOS, Sparkle, and for annotation models, RDF Scheme, and the new version, which was already presented, RDF Star. But we need also to mention specific for the healthcare standards, like digital imaging and communication in medicine, which is one of the core standards for images in healthcare, and a special standard for representing ontologies in healthcare, the Open Biological and Biomedical Ontology OBO Foundry. Healthcare interoperability is quite challenging because we need to exchange healthcare information between different medical devices, between different organizations for administrative purposes like health insurance, or exchanging data for the same patient between different hospitals and clinicals. And we need also to combine patient data from different sources like electronic health records, lab data, pharmacy data, clinical narratives, medical images, etc. And here HL7 and HL7 fire are crucial. Here we provide some sketches of our digital workflow from Catania Hospital, where are presented the main steps for collecting information in biopsy, for digital histopathology, converting this information from physical to digital, and combining the digital information from different medical devices, different slides archiving, and here we can see finally the linkage between the physical slides and digital images in the hospital information system. The medical images contain rich metadata information, which is organized at different groups at different levels, starting from the most general information about the digital slides to more specific, like image formatting, coloring, and organization of those images in hierarchical structures. This metadata actually are enriched additionally with annotations provided by physicians for different image regions, which are annotated manually by physicians when they are diagnosing different patients. And here in our project, we have implementation of annotation system that transforms the input to a variety of standard output formats and provides the metadata in JSON. Combining heterogeneous data from well-slide images, synopses, which actually are textual descriptions of the image interpretation provided from physicians, electronic health records, information for similar cases from scientific publications from PubMed and PubMed Central, additional public data sources, and last but not least, like open data, we can benefit also by using not only the information from BioPortal, which provides several ontologies which are domain specific. Also, we can benefit from encyclopedic data as Wikidata that brings not only the multilingual labels, but also mappings on the concepts of the standard ontologies and classifications to the different multilingual representations. The key issue is multilinguality. Still, the majority of standard ontologies, classifications, vocabularies lack translations to the majority of European languages. The Monarch initiative provides harmonized terminology, integrating data about phenotypes and genotypes, and this is the core ontology which is used as integration of different important vocabularies and ontologies. SNOMAT is one of the widely used ontologies in healthcare, and medical subject headings is important for the annotations of scientific publications. The Unified Medical Language System is another very important vocabulary used to normalize the concepts which are extracted from clinical narratives to standard vocabulary. And the one that have translations on several languages are International Classification Diseases 10th version and 9th version, And medical domain has very rich vocabulary, and all these ontologies are designed to serve different purposes. That's why all of them are important, and it's quite important to integrate all these ontologies and to identify different mappings between them. But still, there is a lack of specific ontologies for certain tasks, and there is a lot of ambiguity between concepts used and different ontologies. For instance, for cancer, are available only for the breast cancer, prostate cancer, thyroid cancer, and upper level cancer ontology. In our specific case, we needed to address such tasks like diagnosis for colon carcinoma, cervix carcinoma, lung carcinoma, and celiac disease, for which we identified some gaps and lack of sufficient ontologies and the vocabulary represented in the currently existing one. That's why we developed a new ontology. It's called XML OWL2 ontology. You can find the current version in Zenodo. And there are also mappings for some standard ontologies available in the newly generated one. It models the clinical cases for all these diseases, including the intervention and locations, which are crucial for histopathology imaging. And one of the main results is development of multilingual, multimodal knowledge graph, which combines information and metadata both from electronic health records, clinical narratives, and metadata from images, annotations from images, which is still in progress, and it covers English, Dutch, and Italian. The current status can be viewed at the link presented above. The knowledge graph actually brings us a lot of benefits. What is the added value of this rich semantics? Some complex relations can be discovered, for instance, searching similar cases among the registry of different patients in the hospital information system, or searching similar cases in the scientific literature, browsing different publications in PubMed Central. This rich semantics allows us to identify such complex relations and to support the decisions of the physicians in complex diagnosis. Thank you for your attention.
Thank you, Svetla. This was impressive. I mean, all those ontologies. My first question is having heard Víctor how much time they spent on this legal data model. What is the time spent in your area on modeling data? Are you in modeling, or is this done by HL7 and DCOM, and then you just translate and make it usable for the toolings that we saw, the comparison, the knowledge graph, and all that?
Actually, we're using in our semantic model HL7 FHIR standard, and HL7 is used for communication between different medical devices. And this is a 4 years project. It took us almost 2 years to reach this stage of the project. And we have 2 years ahead. Yeah.
Okay. So, yeah, but I think this is important for our audience to see. Okay, Víctor has spent at least 1 year with his project in making a data model for legal annotations, and you have spent almost 2 years to create a data model for healthcare annotations. So if a project is now making or trying to advance in the area, if they don't use your results, they will have to spend 2 years more, which kind of shows nicely why we are having this exercise. Because then we run into all kinds of licensing issues and commercial issues, but that's a societal issue. But I think we need to do so. Thanks a lot, because that really is a justification to further explore this route on metadata interoperability. But now we have Piero with us. Thank you, Svetla. This was really impressive. We have Piero with us, hopefully with some sunshine from southern Italy. We see sunshine from the window. So Piero and I, we had a large dispute in a past project over whether to use instance data or categories. You remember that one? And Piero, I already told about our Waterloo when trying to get with linked data technology into a telco who had a real-time database highly optimized, where you said, look, your mental model is nice, Rigo, but go away. we have to deal with this differently. So I remember also that the reasoner was very slow in the beginning, and by throwing out some 1, 2, 3, 4, 5 idiotic requirements, you made it run really, really fast. So Piero, I'm looking forward to your presentation.
Yes, I will actually touch these topics today. But first of all, let me apologize for joining late this meeting. Unfortunately, there was a lecture that I couldn't possibly move to another slot. So actually, more generally speaking, what I'm talking about today, okay, let's see if I can share my slides, is the use. Do you see my slides?
I see a black screen for the moment. Yeah, now I see your screen. Yes, perfect.
Oh, okay, very good. So the metadata and
Piero, your bandwidth doesn't seem very good. Perhaps you switch off your camera, because that will improve things.
Yes. Yes. Okay. So I have to do it from here. Where is it? Maybe here. I can't find anymore.
It's in Zoom. On top of you have on top of your presentation, you have you are viewing blah 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 view options. You have
okay, here.
Yeah, if you click on it, it comes down.
Stop video.
Stop video.
Very good. Okay, so let's go back to the slides. The metadata I'm talking about today contain and encode the privacy policies, consent of the data subjects, and other information that is related to the requirements of the GDPR. The work I'm presenting today started with the previous project special, where Rigo and I were having the conversations as just recalled. Each of these we are moving the results are special to a more mature level, to a higher level of maturity. The final goal is helping what are called the data controllers, so the companies, the entities that collect the personal data and process them, in complying with the GDPR, so as to reach a healthy European economy where the rights of the citizens are preserved. And it is on three main pillars. First, we want to give control to data subjects and to controllers on how personal data are processed. The second is, of course, transparency. We want to facilitate the task of monitoring the use of personal data processing for citizens, for data subjects, and for the data protection authorities that need to audit the behavior of data controllers. And this is possible only if the compliance checking is supported automatically with some computerized system. So the approach, as you see, is, from my word, is typically, it's basically technical. And indeed, Trapeze is supposed to do an architecture like this. Hope you see it. In the top line, you see three color circles that represent the main stakeholders that are the subjects in orange, data protection authorities in green, and data controllers that same in blue. Below that, there is a line of dashboards, applications that are oriented to one or more of the stakeholder categories. And below that, the core of the architecture, which is the business logic, where the business lines of the controllers produce streams of data processing events, some of which have to be for compliance. So they are fed to a compliance engine that makes returns its decision based on the consent and on the policies being stored on a tamper-proof ledger, which is with the blockchain. So this is the overall picture. In this picture, today we focus on a very important component for the business logics. Clearly, privacy policies and consent play a major role and are needed by a compliance engine to work. So this is why we are crafting metadata that contains such policies and consent. They are metadata because they refer to the data. They are not the data. They describe how data is used, if we are talking about privacy policies, or how data should be or can be used if the policy itself is the consent of a data subject. I will use the term data usage policies to refer to both, and to refer also to some extent to very high-level data usage policies that are contained in the regulations, such as the GDPR. Now, what are the requirements we have collected for this kind of metadata? First of all, the language for encoding the metadata should be expressive enough for encoding the fundamental concepts of the GDPR, privacy policy, and consent in a way that enables automated compliance check. So privacy policies have to be compared with the GDPR and with the available consent to tell whether they are compliant or not. The second important requirement is usability. Usability for all policy authors that include both the employers of the controller that have to write the privacy policies and the data subjects that have to configure their consent. Then we need the whole system to be, the whole compliance checking process to be very reliable, because of course any mistake will potentially cause loss of money, maybe significant loss of money. And of course, interoperability, which is one of the major focuses of this workshop. We have different stakeholders. They all have to understand the policy in the same way. When data is transferred from a controller to another, then it travels with sticky policies that specify how the recipient can use the policy. So it is essential to have this common agreement on what the policy means. So it's not only about the standard formats, it also includes the standard semantics. Last but not least, scalability. We have challenging real-time scenarios where compliance checking must be done on the fly. The frequency may reach several thousand compliance checks per second. The main challenge here is satisfying all requirements together. For instance, there is an obvious contradiction between, opposite needs between expressiveness on one hand, scalability and usability on the other hand. So now I'm going to see quickly how Trapeze addresses all the requirements. The first strategic choice is leveraging the vocabularies developed by a World Wide Web consortium called DPVCG, whose task is precisely developing data privacy vocabularies. With these vocabularies, we address, first of all, the expressiveness requirement. This vocabulary covers extensively the concepts of the GDPR, including data categories, legal bases, obligations, technical measures, and so on and so forth. And it also covers some common subterms that occur in many application domains, such as commonly used data categories, commonly used purposes, and the like. The second requirement that we address with these vocabularies is interoperability, because they provide already standardized representation of the above concepts and harmonize previous related initiatives. The second strategic choice is adopting AL2 as a policy language, basically. A profile of AL2 called AL2PL, where PL stands for policy language, and profile means that AL2 is not used entirely, but it is restricted by allowing only some operators that are to be combined in a specific way. The first benefit we get is expressiveness, because it's enough, AL2PL is enough to assemble the terms of the DPVCG into privacy policies, consent, and requirements of the GDPR in a machine understandable way. The second advantage is that AL2 is class-oriented, and here we come on topics mentioned by Rigo. And this is paramount for expressing policies with different regularity. This is, in turn, needed, first of all, to compare privacy policies with the GDPR, because the two have a quite different granularity. Then it is possible to have finely tuned policies. For example, I'm able to say that you can track my position when I'm in Europe, or only when I'm in Italy, or only when I'm in Naples, or maybe in the building of my university, or even in my office. So we have an extraordinary degree of flexibility. And last but not least, it makes it possible to exploit in practice a possibility opened by the GDPR, which is reusing data for similar purposes. For instance, all sorts of commercial interests, something that without classes would always require the judgment of an expert, say a lawyer, to test whether the new purpose is similar enough to the old purpose. And the most important role of AL2PL is that it captures, of the class-oriented approach, is that it captures compliance checking correctly. Basically, if I get an instance-oriented language like RDF or RDFS, it is not adequate, because its semantics has no relationship with compliance checking. So you get results, and besides that, you don't have any of the advantages mentioned above about handling different levels of granularity. Another advantage of using AL2PL is interoperability, because AL2 is a standard, facilitates interoperability, of course, through ontologies written in AL2, the meaning of new terms. Local terms used locally by a particular data controller. Domain-specific terms can be communicated very easily to other parties, and the compliance checking code still works without no need for any changes. It's also very good for extensibility. With this approach, so ontologies for defining the meaning of terms, plus the formal semantics of AL2, which is not ambiguous, guarantee the policies are understood in the same way by all software engines that comply with our framework. This is crucial for compliance. as an example of how easy it is to add new terms, local terms, domain-specific terms, consider this example. In order to recommend art events as a new purpose, you need the first line that declares it to be a class, and the second line that says that it's a special case of service provision, where service provision is the closest term to recommend art events that can be found in the vocabularies developed by DPVCG. The objections are enough to let the reasoner to use this term correctly. Okay, so this is the advantage of semantic interoperability. The other requirement is reliability. Reliability consists of two main properties. One is correctness, which means no false positives. This mitigates the risk of violations, which means risk of sanctioning, risk of loss of reputation. And the second important property is completeness, no false negatives, which means no unnecessary loss of the opportunities of using data in a legal way, which is also something that means money in practice. And L2 again addresses this requirement with its formal semantics that provides a precise correctness and completeness criteria. We are able to prove that our compliance algorithm is correct and complete with mathematical proofs. And again, RDFS is not adequate for this purpose because since its semantics does not match compliance checking, then it doesn't provide useful correctness and completeness criteria for the algorithms. And also scalability. In this case, it is important to use a profile rather than the entire L2, standard L2. Reasoning in L2PL is much easier than reasoning with full L2. We use, moreover, a specialized algorithm for the profile. And with this specialized algorithm, if we implement it with the sequential Java implementation, which is not the most performant technology you may think about, we could still perform a compliance check in just a few hundred microseconds. So we get very close to the performance we need. The challenge here is adding negation for dynamic consent. Rigo is an expert about that. He's one of the inventors of dynamic consent. Because the negation may affect scalability. Basically, negation is needed because for dynamic consent to work, you must be able to say, okay, you can track me in the city, but not when I'm here in this street or in this building. So this kind of extension is needed. The profile and its nice features are also good for usability. From the point of adoption, the specialized algorithm is very simple. Okay, it can be implemented in many languages by the adopters themselves. Our partners have implementation and implementation based on smart contracts and other based on JavaScript. So there are no dependencies on complicated, possibly proprietary black box technologies. Again, from the point of view of usability adoption, we made another strategic choice. So in external policy formats, with which some companies, organizations are already familiar, talking about JSON, URL, and so on. So policies are crafted with these external formats are later converted into the internal L2 format for compliance checking and explanations. The usability of the URL is successfully tested by Thomson Reuters in special. In Trapeze, we have defined a JSON encoding, and I give you a quick idea of how it looks like. We have policy sets that contain the policies of a controller or the consent of the data subject. It is annotated with a list of ontologies that specify the meaning of the terms used in the policy, and there is a context field that looks like the one of JSON-LD. You can specify a default namespace and abbreviations for your prefixes. Then each policy in the policy set has more or less a shape. It specifies which data categories are being processed. In this case, there's both demographic and location data items can be processed. The purpose is marketing. The data can only be seen by company Acme. And the processing applied to the data is a kind of automated decision-making with human involvement. Then if it's where privacy policy, then there will be more fields for adding legal basis, obligations, protection measures, information about storage, and so on. Okay, I hope there are still a couple of minutes left for questions and comments. Anyway, for any further information, you can reach me at that address. Thank you very much.
Thank you, Piero. As impressive as always. Okay, so we are 4 minutes early into our discussion, and Víctor has already the first question, because I had already a question for Víctor. It is so the OWL2 format for compliance, says Piero, and Víctor, you are the chair, one of the chairs of ODRL. Could you imagine that ODRL can be expressed in the OWL2 profile that Piero just mentioned, because then it would make compliance testing easy?
Absolutely. We would really like to hear more from this. I'm aware of Piero Bonatti's academic publications. I didn't know about this Trapeze project. And I wonder if this talk could be shared among the ODRL members so that it can be discussed, because I think it's perfectly compatible to make a transformation from ODRL expressions into this language for compliance. What do you think, Piero?
Oh, it's already been done, actually. One of the participants to the standardization activity for not entire ODRL, but the profile for licensing, which are in many respects very similar to privacy policies, because they put restriction on the usage of data. One of the participants is Ben Whitten-Smith, who is also a startup on this business, and they are also using an ODRL syntax for an internal format, which is our language. So it is definitely possible, it's definitely interesting. And of course, I have not provided all the details. It would be difficult to include all the features of ODRL. Okay. But for specialized profiles with a few simplifications, then the mapping is definitely possible. It can be made unambiguous and then leverage the existing reasoners for how to PL profile for doing the reasoning.
And the second question, very quick, because it's really interesting. This.
No, you don't have to be quick. We are well in time.
Excellent. So my question is, what's the entry point for the resources you have provided? Do you have free resources that can be reduced in order to work with your specification?
Okay. The portal of a project special is already distributing, but you can fetch the implementation.
Thank you.
There. And it also has the old vocabularies already in our format developed by Special. However, they are now obsolete because DPVCG has carried out more work in the meanwhile, and I'm agreeing and contributing to the group to provide an old version of their vocabularies. So, but that's not yet ready. That's not yet ready, but it will be ready from the website of the DPVCG.
Okay.
In the meanwhile, you can use the old vocabularies if you like, or you define your own. And also because if you're interested in ODRL, probably you're more on the licensing side, you need different terms, and you may want to use different ontologies.
Pierre-Antoine, what is the relation between this OWL2 profiles and RDF star? Yeah, I know. But I'm only the lawyer.
Well, I'd say none at the moment. Probably, I must say, I don't know. I didn't know about that specific file before. Very interesting, by the way. Thank you very much for that presentation. But so RDF currently the semantics of RDF star is defined purely in terms of the semantics of standard RDF. And one of the benefits we expect from that is that just like RDF is extended by RDFS and then OWL, RDF star could be extended the same way. Now, without entering into too many arcane technical details, from what I understand, because the semantics of OWL is somehow schizophrenic. There's this RDF-based semantics and the so-called direct semantics. And from Piero's presentation, I take that you're more interested in the direct semantics, right? Exactly. So definitely the link with RDF star is far from trivial. That's all I can say at the moment.
Unfortunately, I had to confirm this. Just for information, the DPVCG has extensively discussed this issue because it would have been extremely nice to have an RDF syntax for privacy policies and consent. Unfortunately, since they are oriented to classes, then to instances instead of classes, it's very difficult to get a representation, a serialization that is both natural and that models correctly the compliance checking. Eventually, we gave up, basically. So now they use RDF for annotating resources without using the annotation for compliance checking. And there is a separate set of guidelines if you want to do compliance checking, how to do it without.
So,
which is more complex than I had wished it would be. My initial idea was simply to use the annotation for compliance checking.
RDF can still be used to connect the data with the related policies, with their data subjects, so to put the pieces together. But you cannot encode the policies with RDF.
Interesting. That means we need a combination. So everybody else is. I'm looking on my 3 screens. I'm looking at all the participants, also those who are just participants in the webinar. And you can put a question into the WOWA chat, or you can just raise your hand, and then I can allow you to talk to the panel and to put up your question. In the meantime, we have a lot of questions from beforehand. So Piotr has put them in a nice. Is he still here? No, I don't see him anymore because he was here in the meantime. He had questions about the leaky metadata, whatever that means. What is? Can we make sure that metadata doesn't leak information beyond what is supposed to disclose? Has anybody any answer to that? Because I think it's a tricky question. We can, of course, decide that, yeah, very nice question, but needs a research paper. So who's with me on that?
What metadata is not supposed to disclose? Huh?
Yes.
Depends very much on, I would say. In our case, privacy policy is something very public. I mean, and its content can hardly be sensitive. So,
but perhaps.
But I guess that that in the healthcare system must be much trickier.
Svetla, has this been considered in your?
Yeah, actually in healthcare, you need somehow to connect all the data from medical images, from devices, from healthcare records, etc. And it's crucial to use identifiers which allow you to do this integration and connection. But especially for medical images, you can't fully, of course, anonymize patient data. And this information somehow, when it's provided by medical devices, can lead to the identification of patient, and it's crucial the metadata which comes from different medical devices somehow to be pseudonymized in order to avoid such linkage of information.
Yeah, in general, I think anonymization has strong limits, because the more we know about reconstruction attacks, the more you have to sanitize your data, and the more there's nothing left anymore that you can compute. So I think that's the different approach that also Piero and I were promoting. Okay, I think the next one is rather for Pierre-Antoine. Automated or semi-automated translation between context and namespaces. Is that already doable, or do we have to extend or do something?
Well, there's an abundant literature on ontology alignment, which is precisely about that, about helping express the links between different ontologies or vocabularies, and how to ideally automatically convert from one to another. So I'd say that this is pretty well charted territory. Not saying that all the questions are closed, but there's a lot of research on that topic.
Would you say that BDVA can play a role by saying, okay, if somebody has already done a translation from here to there, they should be published in BDVA, so that all the projects and can benefit from that?
That definitely brings us to another question, which was raised by Víctor about publishing the data models. That I think that includes the vocabularies and possibly the mappings between the vocabularies. So there's a broader question there. But to finish on the automated conversion between contexts or vocabularies, I wanted to point out again the profile-based content negotiation work, because that's precisely one of the motivation behind this work. By when the consumer requests a given profile, it's expected that the provider of the data knows how to convert their original data into those different profiles. The rationale being that the closer you are to the data, the more knowledge you have about how to convert it across different vocabularies, different contexts, or more generally different profiles. So again, that's the kind of questions that are being considered by this working group right now as we speak. And so anyone interested in those questions should definitely have a look at the work done in this working group.
Can you repeat which working group you mean?
That's the data exchange working group.
Okay, people can contact you or me if they are interested in this.
Yep.
Okay. Then we have data quality, because that's one of my favorite, because we have machine learning where we ingest everything, and then we do machine learning. We can't explain what the machine does, but we believe whatever comes out, which is religion. Data quality is absolutely crucial. And so the question from Piotr was, when I have various streams coming, and I think this is addressing Albert a bit, when I have multiple streams coming on from multiple sources, how do I measure and how do I deal with data quality? So one of the W3C approaches was to say, okay, we label data quality by making it by giving it provenance information. I saw that CDIM had also some extension to it.
Yeah, so the data quality, so practically it should be done already when you have the data provider, and then there should be some processes to ensure, of course, already this data quality. So there should be some pre-filtering mechanisms on their side before they transform the data into the CDIM format. So that means when the data is coming into the cloud storage, the data is already somehow refurbished in some way by the data provider itself. So of course, the question is, what are the standards for setting up these filtering mechanisms on the data provider side? This remains still.
Yeah, but how if I come into and I'm a data consumer and say, okay, I only want data of medical style quality.
Yeah, okay. So in the cross-CPP project, for this, we have what we call a context of the data. So what we are doing is we are analyzing the data in the marketplace and try to figure out how the quality is. Yeah, exactly as you say. For example, if you take a weather provider and he wants to build a weather service, and you all know it, black cars temperature data is not very good for use in weather services. And for this purpose, in our project, we had what we call a context mechanism, which is checking exactly this. So there are some rules behind this whole data, which are semantically modeled to identify somehow the relationship between what the data quality should be and how we can try to achieve.
Yeah, the challenge is really, I think, when I hear Víctor saying we worked 1 year and Svetla 2 years, and Piero saying, oh, we can create a generic reusable policy, then that is a challenge that brings me to a question that Víctor raised: how can BDVA help here? Should we have a task force on interoperability where we can say, okay, when we can reorient people, saying, okay, this is your issue, where bring your issue to our table, we can redirect you. Perhaps there is already somebody working on it. As people come together and we identify a thing where 5-10 projects are having the same challenge, and then we can band together to impose standardization at the venue of BDVA's choice. I mean, that there's many things possible. So really looking at everybody to give feedback here. So please raise your hand if you have any remark on that. Perhaps Anna can also tell us
thank you,
what the
Rigo.
options are.
Yeah, I cannot turn my camera on. Sorry about this. Yeah, I'm listening with a lot of attention, and definitely, if there is a need, I think BDVA could be a good place. But of course, this needs to be further discussed how to implement it. But it could be a task force, or it could be just some kind of space virtually and also physically for experts to discuss, and virtually to share that information, something that we can implement. Yeah, definitely we need to discuss. I don't have the answer because we need to look at more people interested really to create a bit of critical mass, but very much in favor if there is a need and clear benefit for future projects and also for industry. Clearly, we do need to support this.
Okay, we can do something like a call for participation, Pierre-Antoine.
Yes, I just wanted to point out that this is, and Rigo knows very well about this, but this is discussion that's been happening also with some colleagues at W3C. The linked data principles make it possible and easy to create vocabularies in a distributed fashion, so that anyone that needs a new vocabulary can do that. And it's really, Rigo mentioned the metaphor of the bazaar and the cathedral. So it's really a bazaar-ish way of doing things, and that's nice. But at some point, it's also good to be able to crystallize the work that's been done, especially when it took so long in projects. And so, yes, finding a way to capitalize on the work done and to make it easily discoverable and maintained, I think is really something that's needed, and it's hard to find a good home for that kind of work because it's on the same. It's very generic also. So yeah, maybe BDVA could be a good home for that, and I think it's worth discussing.
Okay, we are at the end of our session. We are already 2 minutes time over. I want to thank every speaker because you were brilliant. And you were in time because nobody actually was taking more time than allocated. So perhaps Anna and I will follow up on making a call for participation for some kind of interoperability work, and see if there is enough interest. If there isn't, then it's not worthwhile pursuing. Then we will have interoperability sessions from time to time. But if there is interest in more work, then we may create a platform, Anna. That's, I think, perfectly possible. So, Anna, I leave it to you to close the session, also technically.
I think as the owner of this session, you can already thank everyone, and I will just put a nice video at the end.
Okay, so thanks everybody. We had a nice audience, and we had an audience which was stable over time. So we had a pretty good audience, I think. Thanks everyone, and I think everyone's hungry now. And we with this. Thanks to the speakers, and to the next session. Bye-bye, everybody.
Bye.
Very much. Bye-bye.
Thank you.
Thank you. Bye-bye.